welcome to this course on algebraic geometry and commutative algebra. In the last couple of lectures we have been studying localization of rings and localization of modules. Today I will do some local properties which are also known as local global principle, and this will be very useful in the geometric context. So when I have the geometric language more developed, I will need to use this kind of properties. So let us start with, so I have to recall couple of definitions. So definition. So as usual, let A be a commutative ring and V be an A module. An element A in A is called a non-zero divisor for V. This is a generalization of the concept non-zero divisors in a ring. Now we are talking about a module and an element A in A. When is it a non-zero divisor for the module V? If A times X is non-zero for all X in V, X non-zero. That means A doesn't kill any non-zero element of the module, then we call it a non-zero divisor for the module V. This is obviously A is a non-zero divisor for V. So I will write in short NZD, non-zero divisor for V if and only if the left multiplication by A on V. So this map is any X going to A times X. This map is injected. That means no non-zero goes to obviously 0, but no non-zero X can also go to 0. That's obviously equivalent to that. It's a non-zero divisor. And the set of non-zero divisors the set of all non-zero divisors non-zero divisors for V is denoted by NZD of V. So this is by definition all those elements A in A such that lambda A left multiplication by A is injected. And clearly NZD of V is a multiplicatively closed set closed subset of A. All right. So one more observation I would like to write here. one more observation. So this is, let us call this as a small lemma. That is, let S be a multiplicatively closed set in A, and V be an A module then S is contained in the set non-zero divisors for V if and only if the iota map IVS, this is a map from V to S inverse V, is injective. So proof, I am proving this way first. Assuming that it is a non-zero divisor, I want to prove this map is injective. But that is more or less obvious, because if an element x, so if x is in V, x non-zero, and iota V s of x is 0, this means then x by 1 is 0. That means there exists S in S such that S times x is 0, but this means that S is a 0 divisor for V. So that is, S is a 0 divisor for V, but that contradicts because S is contained in V, but contradiction, since S belong to S which is contained in NZD V. Conversely, so suppose I have given this map is injective and I want to prove that S is a non-zero divisor contained in the non-zero divisors for V. So suppose let S belong to S and S times x is 0 for some x in V, x non-zero. That means it is not a 0 divisor, it is not a non-zero divisor for V. Then what does this condition means? Sx equal to 0 implies this x by 1 is 0 in S inverse V. But then x which goes to x by 1, this is 0 and x is non-zero, x is non-zero and 0 also goes to 0. 0 goes to 0 by 1 which is also 0, both these are 0 in S inverse V. So this proves that is the map iota V S from V to S inverse V is not injective. So that's but we have given it's not injective, so it's a contradiction. So that proves this implication. So this will be useful when we go on to the local global principle. Now I will state this local global principle, which is important. So all right, so that is okay. Before, so this is I will call it a theorem. This is called local global principle. So, let A be a ring always commutative and V be an A module, then the following are equivalent. Number 1, module V is 0. Number 2, V localized at P is 0. Remember here I will just write in a bracket what is V localized at P, this notation. This is precisely if I take the complement of P, that is a multiplicatively closed set, and if I take S inverse of that one, instead of writing this complicated, one simply writes the suffix V. So, this is for every prime ideal P. That means locally at P it is 0 for every P. Okay. Third one, V localized at M is 0 for every maximal ideal. So, let us prove this. See, this is remember that we are going to define a topology there on the spectrum, and this condition means at every point in that topological space it is 0, and this is every point in that close point in the topological space will be 0. This language will come in next couple of lectures. Alright, so how do we prove this? So, proof 1 implies 2 implies 3. These implications are trivial. So, 3 implies 1. Alright, so I want to prove that V is 0 by assuming V localized at M is 0. So, we assume V localized at M is 0 for all M in the maximal ideal of A, and to prove that V is 0. So, suppose on the contrary that V is non-zero, then we are looking for a contradiction. V is non-zero means there exists at least one non-zero element there. So, let 0 not equal to x be in V, and A is the annihilator of this x. What is that? That is by definition all those elements A in the ring A such that Ax is 0, that annihilates x. All those elements of A which annihilates x means they kill x, that is Ax is 0. So, obviously this is a subset of A, and clearly A is an ideal in A. That is because if A is there, B is there, then A plus B or A minus B, they will because both of them kill A plus B, and A minus B will also kill X, therefore they are elements here. Similarly, if A is there and C is the arbitrary element of A, if Ax is 0, then Cax is also 0, that means Ca belongs to it. So, this is clearly an ideal in A, and therefore, and it is because x is non-zero, this element 1 is not in the ideal A, that means this A is a proper ideal. So, that is A is not the whole ring. So, it is a proper ideal. So, we have proved as a corollary to the Krull's theorem that there exists a maximal ideal, at least one maximal ideal which will contain A. So, there exists M in SPM A such that A is contained in M. Alright, but what is given to us? We have given this Vm is 0 for all maximal ideals, in particular for this maximal ideal. Since V localized at M is 0 and therefore, so x by 1 which is an element in V localized at M, this is also 0. But this element is 0 means what? It is killed by at least one element outside this M, because this Vm is the localization, this is A minus M, this is a multiplicatively closed set and we have inverted that, and this is the V, this is S inverse V. So, if somebody is 0 here, that means that element is killed by somebody outside M. So, that implies there exists S not in M. Of course, this S is an element in A such that S times X is 0. Therefore, S belongs to A by definition. So, that implies S belongs to the ideal A, because A is all those elements which kill X. So, S also kills, but A is contained in M, that is how we have chosen our M. But this on one hand S is in M, on the other hand S is not in M, a contradiction. That means V has to be 0. So, that proves our implication 3 implies 1. Alright, now I am going to deduce number of corollaries from here to show you its importance in commutative algebra, as well as I will show you that when we do geometry also. Alright, so corollary 1. So, corollary 1. Alright, so now we have, let as usual our ring is fixed, A be a ring and F is a module homomorphism from V to W. F from V to W be an A module homomorphism. Of A modules V and W. Then I will write a sentence in the words. So, then F is injective. There are many statements together I am writing. I will read it respectively surjective, respectively bijective, respectively 0, then if and only if F localized at M, which is homomorphism from V localized at M to W localized at M for every. So, before that I have to write this, is injective, respectively surjective, respectively bijective, respectively 0 for every m in maximal ideal of A. So, there are 4 statements, if you like, they are combined in this statement. So, I will read. So, F is injective if and only if F localized at M is injective for every maximal ideal, or F is surjective if and only if F localized at M is surjective for every maximal ideal, or F is bijective if and only if F localized at M is bijective for every maximal ideal, or F equal to 0 homomorphism if and only if F localized at M is the 0 homomorphism for every maximal ideal of A. So, let us prove. I will prove the case injective, surjective, and that will also follow the bijective case, and the 0 case also I will prove it. So, all of them are equally easy or difficult. So, proof. All right. So, and I am going to use the fact that this S inverse is an exact, it keeps exact sequences to exact sequences. This is what we proved in the last lecture. So, I am proving this way, I am proving this way, this way. Let us prove injective if and only if F localized at M is injective for every M. So, let us let K to be the kernel of F. This is all those elements x in V such that f of x is 0. And then in the last lecture I showed you how to write down the exact sequence by using the kernel. So, we get then 0 k to V to this f, this is W, this is f. This sequence is exact. Remember, I did not put a 0 here. So, it does not the exactness of this sequence should be checked only here and here. But that is clear because exactness here means this map is inclusion map, injective map, but precisely we have taken this is in fact this is a natural inclusion from this submodule, this is a submodule of V and this is a natural inclusion, and this map exactness here means the kernel of this map equal to the image of this map, but the image of this map is k, and because this is a natural inclusion map and the kernel of this is k, therefore, this is exact. One, this is exact when I localize at, so take any M in the maximal ideal and then we are taking the multiplicative set S to be A minus M and we are localizing at this set. So, then 0 S inverse of k, but remember S inverse of k we are denoting k suffix m to S inverse of V, that is where our notation is V suffix m to W suffix m, and this map is F suffix m. This map is defined by the universal property. In fact, the definition of this map is any x by S that goes to apply f to the numerator and keep that x s as same. So, this is f x by x, that is this map, and we have checked that if the original sequence is exact, after applying S inverse you get a exact sequence. That means if f were in if f were injective, then this will also remain injective. So, one way implication is obviously obvious. So, the remaining actually the most difficult part or most non-trivial part is to prove this implication. So, assuming that this is injective for every m, then we want to prove that f is injective. That means we want to prove this k is 0. So, we know this sequence is exact for every m. That means Fm is injective for every m, that is our assumption, but this is the kernel of Fm, therefore, this has to be 0. So, let me write down that. So, if F localized at m is injective for every maximal ideal m in A, then k suffix f, k suffix m is 0 for every m in the maximal ideals way. And what do we want to conclude? I want to conclude k is 0, but that is precisely what we proved in theorem. So, that implies k is 0 by the above theorem. Local global principle, but k is 0, that means f is injective. This is 0 because this is precisely the kernel of f localized at m because of that exactness of sequence. So, that proves f injective if and only if f localized at m is injective for every maximal ideal. Now, similarly for surjectivity, we have to consider suitable replacement for the kernel. So, note that f from V to W is surjective if and only if co-kernel f is 0. What is co-ker f? That is, co-ker f is by definition the residue class modulo of W modulo the image of f. So, this is 0, that is this residue modulo is 0 means V equal W equal to image f, that is precisely the surjectivity. Now, I will replace the same argument, which exact sequence I will apply. Now, you have the exact sequence V to W f to co-ker f to 0. I say this is exact because this is a residue class module. This is residue, so this is a pi map, this is surjective. So, that means it is exact here, exactness here, and exactness here is here is the image here equal to kernel here, but you see the kernel of this map, kernel of pi is precisely the image of f. That means exactness here. So, once we have this exact sequence, then again we apply the same trick, apply localize this at every m, and then if Fm is surjective, that means the co-kernel Fm is 0 and co-kernel Fm is 0, that so that implies f is surjective. So, the same now use similar argument as above, or as in the case of k equal to ker, and then we prove that assertion about f is surjective if and only if f localized at m is surjective. Now, the bijectivity will follow if we both put together, and 0 being 0, that will follow from the fact that, so for 0 now you note that which sequence is exact. So, f is 0 if and only if V to W, this is f, and from W to W IDF, IDW. Look at this sequence. I say this is exact equivalent to saying f is 0. Why? Because this is exact means exact here, but exact here means, here exactness means the kernel of this map equal to the image of this map, but kernel of ID is 0, and the exactness here means kernel of this map equal to image of this map f, image f, this is 0, image f is 0 is equivalent to f is 0. Now you again apply the same trick. So if f is 0, then this is exact, and then this is exact, that will, then we know that implies V localized at M, W localized at M, this is F localized at M map, and then W localized at M, and this is the localization of identity map, which is also identity map. That is what we have checked. Identity goes to the identity under localization. So if this is exact implies this is exact, but this is exact, that implies Fm is 0. So we have checked that if it is 0, then Fm is 0 for every m, and similarly you can prove the converse. So I will leave the converse, so check the converse. And then with this I will stop here, and after the break I will consider more consequences from this theorem. Thank you.